Good afternoon, Professor Dasgupta.
Yeah, I'm here.
Yeah, we are also here.
Oh,
Yeah, by the time you prepare for starting, that other people, maybe 5 minutes, we will wait for them. We can discuss it.
okay.
Discuss because,
Okay, if there are any questions, we can discuss that, or because I'm
sure,
going
sure.
to essentially start a new topic today.
Yeah,
Having
because Professor Scholes yesterday and Professor Chakraborty today, they
hmm,
have discussed a bit about the linear algebra part and this. I mean, a bit discreetly.
hmm.
So, this is for information. Students may have question too.
Okay, fine. So, are there any questions? So I will actually start from the beginning, but go towards a bit of the results. But are there any questions at this stage? Then let me just start presenting the screen. Okay, was the connection between SO3 and SU2 discussed in the last two lectures? Anytime?
Yeah, it has been discussed.
So,
Hello. Yeah.
is there a question or an answer? I didn't get that. Sorry.
No, no. I was just telling that it has been discussed.
It has been discussed, right? The connection between SO3 and SU2?
Hmm.
Yes, sir.
Okay, so don't need to go through that any longer. And this idea about double cover and so on, I'm just going to ignore that for the time being. Okay, so what I'm going to do,
Maybe you just make a short remark and pass by.
okay. Okay,
Sir, I
then
have a
maybe,
question in
yeah, go ahead.
one of your previous lectures. So, in one of the lectures, you asked us a question about a one-dimensional object which
Hmm.
changes its value upon transformation.
Yeah, right.
Is the angle you are talking about angle with respect to an axis or something?
Sorry, I didn't get your answer.
You asked us a
Yeah, I understand
object
the
is
question, but what was your answer?
angle of a point like, with respect to the any axis. Is that
Yeah, but that's not really a geometrical object, right? If you transform, then both angles would change. So it will not change at all. Both lines would change, right? If you rotate your coordinate system,
with respect to one of the
then you're not rotating the entire system, right? Then you're keeping one thing fixed. That's
okay.
that's not what the kind of thing I mean. A physical object would actually sort of have no reference to an external coordinate system. Okay, the answer to that question simply is something like this. If you stick to only rotations, that is, if your group is entirely the group of rotations, there happens to be nothing else. In other words, okay, so the technical answer to that is the only one-dimensional representation that rotations have is the identity representation. You cannot have any quantity which transforms by any other kind of number. And that's a result which follows from the structure of the rotation group. If you go beyond the rotation
Okay.
group, for example, if you go to the orthogonal group, which has rotations and reflections, then you can definitely have things which have other things like something called a pseudoscalar, right? Something which stays the same when you rotate but changes sign when you
Yeah,
reflect.
pseudo scalar. Yeah.
Pseudoscalars, of course, are no different from scalars if the only things you are worried about are rotations. The only thing you talk about are rotations, then pseudoscalars and scalars are actually identical. Okay? Because there is no possibility of a difference in behavior. Right?
Yes, sir. Only upon parity they do change the sign.
Yeah, parity, which is not a part of the rotation group, parity
Yeah.
reflection, which is basically. So within the rotation group, the only possible one-dimensional representation happens with scalars. In fact, the only possible 3D representation happens with vectors, which is why you have vectors. Okay. And why do you have pseudo vectors at all? You know about vectors and pseudo vectors, right?
Yes,
But
sir.
you don't have pseudo vectors when your symmetric group is rotations. You have pseudo vectors only if your symmetric group includes other things, in particular reflections or inversion. The pseudo vectors also behave exactly like vectors when you rotate. You can't really distinguish between them. So why is the world full of these scalars, vectors, and other of these quantities are basically answered via the representation theory of the rotation group. Okay. So maybe I will just begin now, and I will not rely too much on this presentation today because the presentation, of course, is big and it has lots of stuff, and so I will just talk a bit about some stuff and then move on to Lie algebras, which might interest most of you because you will need that in other cases. So today what I'm going to talk about are continuous groups, and a special kind of continuous group is what is called a Lie group. So what is a continuous group? Simple answer. A group has elements, and these elements depend continuously on a set of continually varying parameters. So if you can parameterize the elements of a group by giving me a set of parameters, not necessarily one, and as I keep on changing the parameters continuously, this group continuously varies, the elements continuously varies, you have what is called a continuous group. Well, and a few examples might make this obvious, although most of these are familiar, so I'm going to quickly go through them. So a translation in one dimension, for example, you can have a translation operator TA, which acts on the coordinates x and gives you x plus a. There the operators are, or the elements of the group are really translations to a distance a, and these depend continuously on a single real parameter a. Of course, if you are translating in 3 dimensions, you will have 3 parameters, ax, ay, az, which will tell you how much you're translating in different directions. You can also talk of rotations in a plane where the amount of rotation you carry out depends, of course, on the angle theta. And that's a single parameter. This is again something which is very familiar to all of you, so I don't really need to go and talk about it again. The more complicated things, okay, please ignore the rotations in the plane line, which I forgot to remove from here. These are further examples. GLNR, well, these are group elements of n by n non-singular real matrices. Of course, that means n square real numbers, but with it's not, if you think of the group manifold of this, group manifold essentially is if you take all these parameters, what kind of space do they reside in? And the group manifold here is almost Rn square. That is for, say, for GL2R is almost R4. But why not the entire R4? Basically because there's one surface, namely the surface at which the determinant vanishes, that's excluded from the set. So if you think of a 2 by 2 matrix as A, B, C, D, AD minus BC must be 0. That's one equation which the 4 coordinates have to obey. So it will be R4, instead of all 4 dimensional real, or instead of all 4 tuples of real numbers. But with this additional constraint that AD minus BC must be non-zero, which means one surface, the AD minus BC equal to 0 hypersurface, is excluded. But you can move continuously in whatever region is allowed, and you can continuously go from one group element to another, which simply means you can change the ADBC continuously, and that's how you change the GLNR elements. Okay, rotation in 3 dimensions. This is a familiar example and surprisingly complicated example. So I will just say a couple of words, if it has not been covered already, about the group manifold structure of GLNR. Has that been covered already? What kind of group manifold rotations reside in?
No, sir.
Okay,
No,
so
it hasn't been.
No, sir.
okay, so let me just tell you a bit about it. It's actually interesting and important and it has important physical consequences. So how do you specify rotation in 3 dimensions? Of course, it's something which you all know. You can specify it in many different ways. Euler angles, for example, 3 Euler angles do the job. But one other way, a very simple-minded way, is that you can specify it by unit vector, which tells you the direction of the axis of rotation and the amount of the axis of rotation and amount of the angle of rotation, right? You just give me the angle theta and the direction of n hat. That's it. That's all you need. So how many parameters does that take? Theta, the angle, is 1. N hat, to specify a unit vector, all you need to give me are 2 of its components, right? Because you know it's a unit vector. Only 2 components will give you the third one. Or you could just give the angles which theta, which this n hat makes with 2 of the axes, or maybe the polar azimuthal angles, the kind which you use in 3D polar coordinates. But anyway, the 2 parameters will specify the unit vector, 1 more parameter for the angle. But how big will the angle be? Okay, this is the question. So this angle of rotation, how big do I need it to be? The answer, a bit surprisingly, it is not from 0 to 2 pi, but only from 0 to pi. And the reason for that is, if you have a rotation which is bigger than pi, what you can always do is, instead of using that particular rotation, you can parameterize it by simply flipping the n hat over to the opposite side, right, and rotate by a smaller angle. Do you get that? Say a 210-degree rotation about an axis is the same as a 170-degree rotation 150-degree rotation about the opposite axis, right? As long as the 2 angles are up to 360 degrees, that's fine. Which is why your angles goes only from 0 to pi. Okay. So one way to specify all possible rotations is simply this. Instead of talking of a unit vector and an angle, you can just talk of a vector whose length is equal to the angle. Is that okay? Because all you need to know is both which direction is the axis in and how big is the angle of rotation. So all you need to do is give me a vector, not necessarily a unit vector, but a vector whose length is equal to the angle of rotation. So how long will that angle vector be? That depends on how big the angle is. But what's the maximum possible angle of rotation here? Pi, right? You will not go beyond pi. Why won't you go beyond pi? The point is, if you went beyond pi, you went all the way from 0 to 2 pi and allowed both n hat, a unit vector in one direction and its opposite direction, then you will actually be ending up counting the same rotation twice. Is that clear? A rotation through an axis, through an angle, and rotation through its reverse axis to 2 pi minus that angle are the same rotations. So you don't want to, when you say group manifold, you want to parameterize every element of the group by points in your manifold. You don't want double counting. It has to be a 1-to-1 correspondence. Okay. And a smooth correspondence, so that nearby points if you have nearby points in your manifold, you will end up with almost identical or very close elements in the group. So how big should you have here? What is the maximum possible size? That's pi, right? So so if you take all vectors in all possible directions, but lengths only up to pi, what set of points do you actually end up occupying? That's the question. Tell me. If you have understood this point, to parameterize all possible rotations, all you need to give me is a bunch of vectors, all possible directions, all lengths up from 0 to pi. So what's that?
Reflection,
Circle.
+1 to -1.
Reflections are not even counted, so we don't care. I'm asking what if you take all possible vectors in all possible directions, but the lengths are bounded by pi. Of course, a vector is the same as a step, right?
Perimeter of a circle.
Circle. Are you sure? All possible directions, remember. This is a 3D situation. All vectors of all lengths up to a limit. What do you get?
Surface of a sphere.
Let's be careful. Do you mean a sphere
Surface.
or a ball? You know the distinction, right?
Yeah.
A sphere is a set of all points at a constant distance from the center. The ball is all points inside as well. So what are we talking about here? A sphere or a ball?
A ball.
We are actually talking about a ball, right? Because if the rotation is to an angle smaller than pi, it will be a point inside the sphere, right? So it's basically all points inside a sphere of radius pi. That's how you parameterize all rotations. But there is a catch, and the catch is this. Okay, let me just forget about these steps and let's quickly go on to. Okay, so the group manifold of SO3 are 3 by 3 real matrices, orthogonal matrices, which rotations actually stand for, is a sphere of radius pi, but with one important catch, which is stated here. The point is, if you take a point on the surface of this sphere, that's a rotation through an angle pi, right? But a rotation through an angle pi about n hat and a rotation through an angle pi about minus n hat, the opposite axis, are exactly the same rotation. Is everybody sure of that? If you rotate about the x-axis, positive x-axis through 180 degrees or negative axis through 180 degrees, you will end up with exactly the same rotation, right? Is that clear to everybody? Which is precisely why you don't go beyond 180 degrees, beyond pi, because then you are going to repeat. But even at pi, you are going to just repeat those two. Okay? Is there any question about this?
That part is clear, sir.
So which is why the group manifold is not really a ball. It would have been a ball if all points on the ball would have corresponded to different rotations, all different points on the ball. That happens for every point inside the sphere. That is, all interior points of the ball, no problem. They correspond to a unique rotation and only one rotation. And different points correspond to different rotations. But when you go all the way up to the surface of the sphere of radius pi, two opposite points actually on the surface actually stand for the same rotation, which means that the group manifold of the rotations are actually more complicated than what we talked about. It's not a ball. It's not just a solid region. It's a ball with a special topological property that opposite points on the sphere have to be treated as the same point. Only then, if you distinguish them as two different points, then you have a problem. Then different points in your group manifold lead to the same rotation. That's not allowed. So your group manifold is really a much more complicated topological object. The entire interior of the ball, fine, but sphere with opposite points identified. And that actually makes it a very interesting kind of structure. This is a formal name, but let's not worry too much about the nomenclature. Now, this particular group manifold, just imagine a solid ball, but imagine somehow that points right on opposite to each other on the surface are actually the same point. So this group manifold is connected. That means if you take any 2 points in this manifold, you can always draw. Manifold is just a set of points, nothing very special about that. So if you haven't heard that terminology before, it's just a set for the time being. So if you take 2 points on this manifold, you can always draw a curve or a line joining those 2 points while staying within that manifold. You don't have to leave it. You stay within it and you can draw a line joining 2 points. Of course, if you had 2 different balls, then you couldn't possibly draw a line joining them, joining a point here and there. Then you would have to leave the system. Here you can draw a curve without joining any 2 points without leaving the curve. That's what connected means. And the important point here is, can you shrink closed paths down to a point? Now, this is a very tricky and funny thing. So I'm not sure whether you've seen this before, but let me just quickly give you a extreme crash course in topological aspects here. Suppose you have a plane and a plane with 1 point taken out. Okay. Do you think that the two would be identical in all ways? After all you have done is you have taken 1 point out of infinitely many points, right? So it looks like the two are very similar. But let me just point out one very big difference between the two. Okay. So suppose you have this plane, this sheet of paper, and from which I have removed this 1 point. And on this side, let's say we have the sheet of paper without any gap. So here, if I drew a closed curve, oops, I have this stroke recognizer sitting here, which ensures that every closed curve I draw becomes a circle. But anyway, a closed curve here, and let's say another closed curve here. There's a big difference between the bunch of all closed curves on the right hand side, where you have a plane, and all closed curves on the left hand side. Can you see what the difference is? Any closed curve on the right hand side I can shrink down slowly and slowly, continuously, until it becomes a point, right? This one, all of them can be shrunk down continuously until it becomes it stays a closed curve throughout. It's not broken up. It slowly shrinks down to a point while staying entirely within your region. You can do that for this closed curve here and make it shrink down slowly to a point. This one also. Okay. This one, on the other hand, you can keep on shrinking down, but you cannot shrink it down to a point without crossing the forbidden region somewhere, forbidden point, this cross somewhere. What that means is, here, all closed curves cannot be. So in the language of topology, you say the homotopy group, or the fundamental group of this one is trivial, of this one is non-trivial. I'm not going to go into more details simply because I don't have much time right now. But let me point out that for our particular group of interest right now, the rotation group, or SO3R, I'm sure everybody here knows that SO3R is the rotation group, right? The set of all 3x3 orthogonal matrices with determinant 1. There we have this funny thing that the group manifold is connected. You can join a point between join a curve between any 2 points. But, well, here you see we are saying some closed paths are contractible. You draw a closed path in the ball somewhere, no problem. Within the body of the ball, you can draw a closed curve. And of course, since the ball is solid, you can keep on shrinking the curve down without ever leaving your group manifold and getting to 0. What that means is, if you have some process by which you did a bunch of rotations one after the other and ultimately came back to the original thing, you can keep on shrinking it down until this shrinks down to no change at all. What that means is that if you keep on rotating all the way, you will have to come back to no change whatsoever. However, and this is very special, this path, the path I've drawn here, does this look like a closed curve to you? This solid line. Is this a closed curve? What is a closed curve? A closed curve is something which begins and ends at the same point.
It has to be closed because the
here it is closed, right? Because you have to remember that opposite points are actually on the surface of the sphere are actually the same point. This is closed, but now there is no way you can shrink it down to a point without breaking the curve, right? Because the moment you try to move away from this point, suppose you move away from this point here on the surface, but if you are going to maintain the curve, this other point will move this way, just to the opposite point of wherever you land up. Otherwise, the curve will not stay closed. You try bringing this point P, this point to this point by going right through the manifold, which you can of course do because the manifold is solid. You can go inside as well. However, the moment you go inside, it's no longer a closed curve. So I'm breaking the curve in order to make it, to shrink it down. Okay. So this path is not contractible. So this is a special kind of manifold where some paths are contractible, some paths are not. This one, on the other hand, where you go from P to P prime, and then from P prime to P, right, which is actually again a closed curve, is still contractible. You can figure that out. In fact, any curve which goes round the manifold twice this way can be shrunk down to zero. But this actually has immense repercussions. I'm just saying this. I'm pretty sure somebody or the other during this series of lectures might also mention this. They might talk about spinors and why you have special kind of situation in rotations, that a 360-degree rotation is not really identity. 720-degree rotation is. And in case anybody that's has not seen this before, I would definitely recommend looking up the belt trick, Dirac belt trick, or Dirac, yeah, that's what it's usually called, which essentially demonstrates that a 360-degree rotation can be continuously unwound to nothing, no rotation at all, but cannot be always. A 720-degree rotation can always be continuously taken down to no rotation, which is the reason why you can actually have, well, spinors. Remember, spinors are things two-dimensional. Okay, just one more quick question. In the classical world, do you have any two-component object? That is, any object that you know about in the classical world, where our classical world, essentially we deal with the rotation group all the time. Do you know of any two-component object in the classical world, something which is described by two numbers and only two numbers? Not more? When I say classical world, I mean our full three-dimensional world, not something which is confined to a plane or something. Any example?
Spin, maybe?
Spin is, okay, I said classical world,
Oh,
right? Spin, one of the major reasons why spin is so confusing, apparently, is that spin looks very much like a classical object, that of rotation, right? It looks like angular, it is angular momentum in a sense, but there's something very non-classical about spin half. Spin one is perfectly classical. That's exactly the kind of rotations that we have all the time in our 3D world. Can anybody tell me why spin half is so different from spin one, and something which makes it impossible to have a spin half system in the classical world? Why we had to wait till quantum mechanics to get that? I'm sure everybody knows the answer, but
In
maybe
spin
not.
half system, by 2 pi rotation, the wave function exactly gets to the opposite. And
Yeah,
by
so
4 pi
basically that's exactly the point. In fact, for the rotation group, because of this particular structure, that you have paths which are not contractible, so full rotation may not end up being the identity. Okay, I'm not going to go into the details of this, but I'm pretty sure you should be able to read up on this. The connection between the topology of the rotation group and the fact that you have spin-half systems at all. The point is, no matter what system you have, a 720-degree rotation, a 4 pi rotation, can always be undone to the identity, can always be continuously shrunk down to no rotation at all. Which is why spin half, classical world, quantum world, everywhere, a 720-degree rotation or 4 pi rotation is always identity. Whereas, precisely because of the presence of these kind of non-contractible paths, close paths, you actually have situations where 2 pi rotations are not the same as identity rotation, which happens for spin halves, spin 3 halves, and so on, but does not happen in the classical world at all. Because in the classical world, if you go all the way around in your coordinate system, you have to have the same thing back physically. In the quantum world, of course, the fact that the spinner picks up a minus sign does not really bother us, because when we take the mod square, the minus sign goes away anyway. Okay, so, and you should realize that the fact that you have only spin half, which are spins which are half integers and odd half integers, something which I've worked out from the angular momentum algebra, of course. Well, it's easy to see that that has to happen, because if you had any other value of m other than half integers or odd half integers, then if you went round to have angle of 4 pi, the phase you would pick up, which is the im 4 pi, would not have been 1, right? The fact that 4 pi rotations are always contractible, and hence 4 pi rotations must give you the same result as no rotation at all, is a very important consequence. So this fact that you have only spin halves or integer spins is really, okay, it follows from the angular momentum algebra, but you can also think of that as a consequence of the fact that you have this this special structure for the group manifold. Okay, now let me just, since SU3, SO2, SU2 connection has been talked about, I will just quickly just tell you only one thing about it, just skipping all this stuff, because which is essentially well known to all of you, I guess, at least some of it is. Okay, one thing, SU2, of course, is a set of all 2 by 2 unimodular matrices. So can anybody tell me what is the group manifold that you can have for SU2? Anybody knows the answer?
S3.
S3, you know the answer, right? That's good. However, do you know why is S3?
Because from the relation alpha square plus beta square equals to 1, we can actually have the equation of a 3 sphere.
Right. By the way,
alpha is a complex
I hope
number.
everybody has realized why this is true. That the most general form of SU2 has to be an SU2 matrix, of course, is 4 complex numbers, right? It's a 2 by 2 complex matrix, so it has to have 4 complex numbers. Why this particular form, alpha beta minus beta star alpha star, and mod alpha square plus mod beta square equals 1? Everybody knows that, right? Of course, a question like that means that if you don't know, please speak up. Okay, I'm assuming that everybody either knows or can figure this out. So, of course, as was stated right now, this condition alpha mod square plus beta mod square equals 1 is a condition between 2 complex numbers, but since you can always write alpha as x plus iy and beta as u plus iv, that essentially shows that every SU2 matrix of this form basically can be written down into the 4 parameters x, y, u, v with one condition, x square plus y square plus u square plus v square equals 1, which is nothing but the equation for S3, a 3-dimensional sphere, which is a sphere embedded in 4 dimensions, but a surface of 3 dimensions, right? And the important thing is, there is a homomorphism between SU2 and SO3, that's something which must have been discussed today or earlier. But what you have here is SU2 is very distinct from SO3 in the sense that it's simply connected. All closed curves are essentially curves on the surface of a sphere. You can easily show that they're all contractible down to a point. Or you can intuitively think of having a rubber band stretched on the surface of a sphere. Can you shrink it down to a point? Of course you can. That, of course, illustrates that that S2 is simply connected, which means all closed curves on S2 can be shrunk down to a point. I'm just asking you to sort of extend that imagination to S3. So SU2 is a simply connected group which is homomorphic to SO3R, and that is why there is this big connection between SU2 and SO3R. You may often hear the word universal covering group. I'm not going to go into the technical details, but this is basically what the connection between the two really is. Okay. Now, are there any questions about this particular thing? Otherwise, I will move on to a more general thing about Lie algebras. I'm, of course, rushing a lot. Given my past track record, I have to rush a lot. But any questions? If none, let's move over and talk about Lie groups and Lie algebra connection in general. And here I'm going to sort of lie and distort things a bit. I'm going to oversimplify things a bit for the simple reason that I don't have the time to actually continue the whole thing. But let me just try to do it as fast as I can. Now we have been talking about continuous groups. And what is the difference between a continuous group and the Lie group? The basic idea really is that when you have a sorry, I need to actually start at the beginning. Suppose you have a group which is parameterized this way. So G alpha is a bunch of parameters. I have already written that down, so why not use it? So we have group elements which depend smoothly on a set alpha of parameters. Now, one thing which is not written here is what happens when you multiply two such group elements. You get G alpha times G beta. Alpha is not one parameter. Alpha could be a set of parameters. Okay, so alpha could really stand for alpha 1, alpha 2, alpha 3, and so on. Similarly, beta stands for beta 1, beta 2, beta 3, and so on. So what must happen? When you multiply two group elements, you must get a group element. So that group element, which is a product of G alpha and G beta, must be another group element. So must be something for which the parameters take the value gamma, right? And so this gamma has to be a function of alpha and beta. Of course, this is a shorthand notation where gamma actually stands for R different parameters, where R is the number of parameters you need. And this function is really R different functions of R alphas and R betas. But this is just a compact way of writing that. Okay. So if this function is analytic, that is differentiable as many times as you want, then you have a Lie group. Okay, I am actually mangling the definition a bit, but this is effectively the definition for all practical purposes. A Lie group is a continuous group where the group elements depend continuously on a set of parameters. But the composition rule which the parameters obey could be a complicated composition rule, but it has to be a smooth combination rule. That is what is called. That is what happens when you have a Lie group. Okay. Now, of course, you can realize that given a set of parameters, if you transform to another set of parameters in a invertible fashion, that is, instead of using alpha 1, alpha 2, alpha 3, if you have some kind of function which gives you new values, alpha 1 prime, alpha 2 prime, etc., but which you can come back from, then you are not really changing the group structure. You can just reparameterize the thing in many ways. So you have a choice of parameterization, and that is actually very important. It's not just one parameterization, it's a choice, okay, that you can make. So one choice that is universally made is that you choose your parameters in such a way that alpha equals 0. Here, of course, it means alpha 1, alpha 2, alpha 3, all of them equal 0, right? Alpha I equals 0, where I goes from 1 to all the way to R. That stands for the identity. So the identity of the group is always represented by a set of parameters which is 0. And if you think of any representation of the group, then of course G alpha will be represented either by linear operators, if you are using an operator representation, or matrices, if you are talking of matrix representations. And these matrices will also, of course, obey that D alpha for alpha equals 0 must be identity. So given the parameters alpha 1 to alpha r, you get a unique group element. And for a given representation, that will give you a representation matrix. So basically you have a situation where you have a function between R parameters and matrices. So if you change your R parameters, you are going to get different matrices. In particular, when the parameters are all 0, you are going to get the identity matrix. So, but now you have to realize that here you have this smooth connection between the parameters and the group elements, and hence between the parameters and the matrices. So what that means is that if you are going to change parameters from 0 to an infinitesimally small value, so to some d alpha, of course d alpha here means d alpha 1, d alpha 2 and so on, you will of course get a matrix which is not the identity, but which is close to the identity, right? And so what you get is the identity which you would have got for d alpha equals 0 plus a first order correction term in d alpha. So d alpha 1 x1, d alpha 2 x2, d alpha 3 x3 added up together. A factor of I is thrown in by phases and only phases to facilitate the connection with quantum mechanics. Mathematicians usually don't have the I. So if you're reading a mathematics book on the connection between Lie groups and Lie algebras, you may be thrown by some signs. The some signs may very well differ simply because physicists mandatorily put in an I here, which mathematicians usually don't, because mathematicians don't really care. The reason why physicists do that is, for physicists very often these are operator transformations, and you would love the operators, especially in quantum mechanics, to be unitary. And if they're unitary, then if you throw in an I here in the definition, then the XA becomes Hermitian. Because physicists love Hermitian operators and they have nice physical significance for us, we usually like to have the I. Mathematicians often don't care. So for mathematicians, of course, even if they wanted unitary representations, which they of course would very often, then XA would be anti-Hermitian, and they have no problem with anti-Hermitian operators. Okay, but physicists usually put in an I. And of course, this is only the first order in the Taylor expansion of capital D, just the first order in D alpha. There will be higher order terms which are written by dots. And just like in a Taylor expansion of a function, what is XA? XA is nothing but derivative with respect to alpha A of this matrix or operator, whatever you have right now. I'm using operators or matrices interchangeably because you could either talk of the abstract operators or choose a basis and talk of matrices. So I'm not going to distinguish between the two right now. You differentiate d alpha, the function, with respect to alpha A, and put alpha equals 0. That gives you the first order term, right? That of course would have given you IXA. So to get XA, you have to multiply by minus I. Again, that's because you insisted on an I here. So this is how you get the XAs. Now many possible choices for parametrization are there, as I've said. And one very important thing is this, that this is that you can always choose a parametrization such that you can find a subgroup which depends only on one parameter out of the many parameters you have, and where that parameter is additive, in the sense that when you compose two group operations, the resulting parameter is just sum of the two parameters. Now, this may sound a bit complicated, and of course I am not explaining this as thoroughly as I would have wanted to, but let me just ask you, for rotations, can you think of a situation where rotation simply added? The parameter would be just the angle of rotation. And can you think of the situation where rotations would simply add? When would rotation? When? Sorry.
When the rotation angle is very small, infinitesimal rotation.
Well, no, that would also not be really additive. The real thing would be if it's simpler. It's when you rotate about a single axis. No, it's when you rotate about one single axis, right? Then what happens? If you rotate by an angle θ1 followed by rotation by an angle θ2, what happens? You get θ1 plus θ2. Remember, the simple composition rule does not work for all rotations, but it works for this one parameter subgroup. If you just think of rotations about one axis, then you have only one parameter, right? Now you no longer have to worry about the axis. The only parameter is the angle. There's a one parameter subgroup of the set of all rotations. Of course, there are infinitely many such one parameter subgroups, one for every axis of rotation. But these one parameter subgroups have this simple composition rule where the angles just add. Now, just think of a very similar thing that we have. This, you all know what this is, right? Yes? This is just a fancy name for a group which essentially keeps x1 square or x0 square minus x1 square invariant. Instead of SO2 would keep x1 square plus x2 square invariant. SO11 essentially keeps this invariant. So what group are we talking about? Lorentz group? Lorentz group in one space, one time dimension right now. Of course, we could talk about the full Lorentz group, but let's talk about the simpler version. In the Lorentz group, in SO11, okay, in this simple Lorentz group, what is going to happen? You know how to compose two Lorentz transformations, right? Along the same boosts along the same axis. But does the parameter is the velocity, right? Or beta, v by c. Do they add? That is, if you do beta 1 followed by beta 2, do you get beta 1 plus beta 2? You don't, right? You get beta 1 plus beta 2 by 1 plus beta 1 beta 2. That's the famous velocity addition rule. Yes. U plus v by 1 plus uv by c square. Right? That's how the group parameterization works. So this is not additive, right? But I'm pretty sure most of you know about this, that you can change over to another parameter which is additive. If you do two successive Lorentz boosts in the same direction, that parameter adds up. Do you know what that parameter is called? Any idea?
Rapidity.
That's called rapidity, right? And the only reason why I bring this up is to sort of give an example that even if you had a one parameter subgroup, here boost along the x-axis. If you compose two boosts, you get a boost. Fine. This is just basically a one parameter subgroup, just parameterized by one single parameter, the beta or the velocity. But the composition rule here is not additive. It's not beta 1 plus beta 2. For very small betas, it is beta 1 plus beta 2. But for large betas, I'm not worried about large betas. For large betas, that's not. It's not beta 1 plus beta 2. Large, of course, means close to 1 or not infinitesimally small. Okay? So for large betas, it is not beta 1 plus beta 2. But you can go over to a new parameter phi such that the new phi for a composite thing is phi 1 plus phi 2. Okay? Clear? So the point is, this is a statement which takes some amount of effort to prove. It's not absolutely trivial, but it's not very difficult, but you can prove it, but with some effort, that for every Lie group like this, you can always find a parameterization such that the parameter adds. Now, why is that interesting? That's interesting for us because now, if that happens, for that kind of choice of parameters, if you have a large parameter alpha, you can think of that as being built up by n applications of alpha by n, right? Is that okay? Notice that for this, the additivity is important. If you had talked about, say, Lorentz boosting by the parameter beta by n times, you would not have ended up with a final Lorentz boost of beta. Do you get that? Well, as simple as doing beta by 2 times gives you beta by 2 plus beta by 2 by 1 plus beta square by 4. So it does not give you beta, right? But if you say you want to repeat alpha by n times and you get alpha parameter, get to the parameter alpha, that would mean that you want to insist that the composition rule is such that when you carry out a transformation with the parameter alpha 1, then alpha 2, you get alpha 1 plus alpha 2. This additivity is important. And what you can show is that for one parameter subgroups, you can always find a new parameterization for which this additivity will hold. This is a technical point, but this is a very important point. If you didn't have that, you couldn't do the next very important step, which is this. This is simply this, that if you have a parameter alpha, which is not infinitesimal, what you can do is make the parameter alpha, which of course means alpha 1, alpha 2, alpha r, are such parameters, break it up into n pieces. Now if n is very huge, you have an infinitesimal transformation. Actually, in the limit n goes to infinity, this is infinitesimal. So then it becomes 1 plus I, d alpha a becomes alpha a by n. So alpha a by n xa, this raised to the n. And I'm pretty sure everybody here knows this, right? This very famous limit is e to the power x. Everybody knows this, right? Yes? So this is how you end up with this exponential form. So are there any questions about this? So basically what you see here is this. The group elements can be represented by matrices or operators, and because for a parameter choice of 0 you get the identity, for an infinitesimal parameter choice you must get identity plus a small correction term, and this is how you define what are called generators of the Lie group. Okay, so generators essentially tell you what happens when you shift from the origin of parameter space slightly. So your parameter changes to a small value, but the important thing is you don't have to stay confined only to small values to see the effect of the generators. Because of this result, you can say that all group elements can be sort of written down in this form. You the I alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 and so on. Okay, here. But there is a catch which all of you realize, that you multiply two such group elements. These are two different group elements, alpha 1 x1, alpha 2 x2 and so on. This is beta 1 x1, beta 2 x2. Of course, here summation, I'm using the summation in convention. I did not mention that, but I'm pretty sure most of you already understood that. When I write alpha a x a, it's alpha 1 x1, alpha 2 x2 up to alpha r xr. That's the convention. Okay. So if you did multiply these two operators, these are two finite group elements now. Okay. Or really operators representing two finite group elements. I will definitely not get, or I will not definitely get this. I might get this for abelian group, but for non-abelian groups, I definitely will not get this, right? Because exponential operators no longer obey e to the a, e to the b is equal to e to the a plus b. In general, right? But notice that because this is a group element, or this is an operator representing a group element, this is an operator representing another group element, their product, according to the standard representation theory, must be an operator representing another group element. So it must be of this form. The gamma 1, gamma 2, gamma r are function. Of course, these gammas are functions of alpha and beta. And this function has to be a smooth function. Is this clear?
Professor?
So, yeah, go ahead.
Can I ask a question?
Yeah, go ahead.
In the previous fact where you took the limit n tends to infinity,
Yeah.
1 plus I alpha divided by n.
Yeah.
Isn't that we are implying the successive rotations by multiplying the 1 plus I alpha n
No.
x alpha?
Well, I'm implying that you have an additive behavior for the parameters.
Additivity comes from. I mean,
No, that's what I said. I didn't prove this. I stated that you can always reparameterize to find a set of parameters for which the rule is additive. For one parameter,
in
not
that case,
for
alpha A is the parameter we're looking for, or if alpha A can be anything general, right? Because
no, it can't be anything general.
rotation R1
No.
multiplied by R2 is another rotation. Then
True, but
successive
that
rotation
doesn't work, right?
then
That's not a one parameter subgroup. For rotation group, in particular, the one parameter subgroup is rotations about a given axis. For that, of course, this works. Let me just say, okay, I will not prove the result for you simply because it takes a lot of time to prove this one result, that you can always find an additivity. But let me remind you that even for rotation, say the standard rotation that you do use this, right?
yes.
This is actually exactly this thing. As long as you keep your n hat fixed. What is this? This is actually a limit as n goes to infinity of identity minus I theta by n hat dot j to the power n. N hat dot j rotates about one axis. For rotations about one axis, the parameterization is already additive. So n applications of theta by n gives you theta. Okay. For other groups, like for example for the Lorentz group, you wouldn't get this simple result if you were using the parameterization beta. You would have to use a different parameterization via rapidity. But the important thing is you can always find such a parameterization. This is something which I have not proven. It's simply a statement for the time being. I'm of course keeping many of the proofs. This is a result which can be proven with reasonable degree of simplicity, but still it will take some time, a lot of time to prove it. So I'm just skipping that. Okay. So you are right in the sense that this is not trivial. This is a non-trivial thing that you can always find a parameterization in which along one axis you can always find this. The important thing is alpha AXA, if you think in the terms of rotation group, alpha AXA and beta BXB, they would be essentially like n1.x.j and n2.j, right? And that would mean rotations about two different axes for which you don't have additivity. It's only additive along one parameter subgroups, not for the entire group. So now that we have this, what does this imply? This fact, but it does imply one thing. If you take two group elements, or actually operators representing group elements and compose them together, apply one operator after the other, you must get an operator representing a group element. This is basically what homomorphism is all about. So what does this demand tell you about the structure of these operators XA, XB? Okay. Once again, the full proof of this is lengthy, so I'm going to give you a shorter version, which is, okay, I'm essentially quoting Georgi's book here. I'm sure most of you know about this book. It's called Lie Algebras in Particle Physics. You will find this proof there. This is not a very mathematically rigorous or complete proof, but this will serve our purpose for the time being. Of course, if this is I gamma c x, what is I gamma c xc then? If this is true, then you can take the logarithm of this thing and you will get I gamma c xc. And just to help us out here, what I'm going to do is add I and subtract minus I, so that this becomes log of I plus k, where k is this whole thing. Why do I want that? Because log of I plus k, of course, can be expanded in a power series, right? K minus k square by 2 plus k cube by 3 and so on. By the way, these series work also for operators. Convergence issues are sort of taken care of if you do this carefully, but I'm not really going to go into all that. Okay. So how does this help? Well, this of course is correct only to quadratic order. So quadratic orders in alphas and betas, higher order terms of course have not been taken into account here. I've just written up to quadratic order, but you could of course go to higher orders as well. Now, this is k, right? K is simply this part, the part whose logarithm you were taking, except for this I. So now what you do is just let's write down this is I alpha A xa. I'm writing it down in full. Is I alpha identity plus I alpha xa minus half alpha xa whole square plus higher order terms. I'm not writing the higher order terms simply because right now I'm only sticking to quadratic order and seeing what I can get. I do the same for the I beta b xb, again up to quadratic order, plus higher order terms, minus the I, and then collect all of them together. So the I cancels. Remember, when you multiply them together, what do you get? I times I gives an I which cancels with this minus I. I alpha xa times the identity times I beta b xb gives you this. This times the identity gives you this. This times the identity gives you this. There's only one other quadratic factor that you get, which is the product of this with this, which is minus alpha a beta b. This is where writing a different dummy index for this too actually pays off, right? Alpha xa can be, this can also be, could also have been written down as beta a xa, but writing it as beta b xb is good because in anticipation of this product you get minus alpha a beta b xa xb. The order is important. Note that I am not changing the order of the operators anywhere. So everybody is with me so far?
Yes, sir.
Okay. So now that I've written this down, what is I gamma c x c? It has to be k minus k square by 2 plus higher order terms. K is just this, right? So, sorry, why do I keep on writing the I? So this is the k. I've just rewritten this thing here. Okay? And then I have to square the k and divide by 2 and subtract. That looks like quite a complicated thing to do, but remember, if this is what your k is, and we are only keeping up to first order, or sorry, second order, then it's very simple. Then the only term that's going to contribute is going to be the square of this one, right? Any other term that you get will contribute to a higher order. When I say contribute to quadratic order in alpha, I mean alpha, beta, they're all of the same order, quadratics in that. That's the square of this, right? So this is the only other term that you get. So you have to, well, you had a I alpha a plus beta a xa squared is going to be minus alpha a plus beta a xa whole square. But you have minus k square by 2, that gives you a plus half here. Okay? Now notice, this piece will survive. But the other pieces, this one and this one, for example, essentially try to cancel out whatever you get when you square this, right? But what do you get when you square a plus b? If you actually had a square plus b square plus twice ab, then everything would have cancelled out. But you don't get that. Get plus ab. And if you keep that in mind, when you square this, this will cancel with this will cancel with this. But you will get half alpha a beta b xa xb. So this will not completely cancel. Plus half alpha a beta b xb xa. So when you carry out the subtraction, what you get is this half alpha a beta a xa, which is already there, this term, plus this additional piece. Okay? Yeah? Of course, there are higher order terms. But let me point out that at this stage, what should be clear is that if you actually want to ensure that this thing is of the form I gamma c xc, which it has to be, right? It has to be some linear combination of the xc's. The only way that can happen is that if this commutator of xa and xb has to be a linear combination of xc's. No other possibility, right? You get that? If the commutator of xa and xb could not be expanded in a linear combination of xc, then the left-hand side would not have been a linear combination of the x's. But it has to be, because after all, the product of e to the I alpha a xc and e to the I beta b xb has to be e to the I gamma c xc. So the log has to be a linear combination of x's. Is that okay? So this is what essentially tells us that
Yes.
for every representation of a particular Lie group, you must end up with this fact, the operators must end up giving you this structure. That XA, XB commutator has to be IFABCXC. And since the composition rule is independent of which particular representation you're talking about, has to be the same for all, because it essentially follows from the group elements, right? Not from the, what these gamma C's are going to be ultimately, that follows from the composition rule in the group. Every representation has to obey the same composition rule because it has to mimic the group multiplication rule. That's what representations are. Which is why you must have this demand that if you linearly combine, if you take the commutator of two generators, you must get a combination of generators, nothing else. You cannot get anything else. And this, of course, brings us to these constants in front. These constants, of course, depend on A, B, and C. And these are called the structure constants of this particular Lie algebra. This is what the Lie algebra is. The commutators close. Once again, the I is something which faces put in. Why do they put this in? Because in particular, we would often love to have Hermitian generators. Of course, if you have Hermitian generators, then this will happen, right? This is not XA, XB. This is negative of X. So XA dagger has to be XA, XB. But the adjoint of XA, XB is not XA dagger, XB dagger. It's actually minus XB, XA. So the I is put in to ensure that FABC come out to be real if you have Hermitian generators. Is it okay with everybody? So this is how a Lie algebra arises out of a Lie group. The basic idea is this, that if you look at the identity element that is parameterized by 0, if you move very close to the identity element, you are going to get the identity operator plus a small correction. This gives us the notion of the generators. And because combining group elements must give you a group element, that immediately gives rise to this statement that the commutator of the generators has to be a linear combination of the generators. So this operation XA, XB commutator, that of course gives us a group element from two group elements. We can define this to be the product. In fact, this is defined to be the so-called Lie product. And all we are saying is that you have an algebra here because it's closed under, it's not only a vector space, the x's are operators, and operators always form a vector space, right? But here you have a product under which the operator space closes. That is, you multiply two operators. In this sense, this is the XA, XB minus XB, XA product. And in this sense, you have a closed set. Okay. So now we have an algebra where the multiplication is a special kind of multiplication called the Lie product or Lie algebra. This is what gives rise to this Lie algebra. Essentially, if you look very close to the identity and only close to the identity, a Lie group goes over to a Lie algebra. Okay. Now, let us quickly go to some basics of Lie algebra structure theory, which we will need perhaps to understand the rest of the course as well. One identity which all of you must be aware of is this one, right? Of course, when I make a statement like that, I'm hoping that everybody knows this one, that if you take XA, XB, XC and cyclically permute ABC, you're going to get 0, right? How do you prove this? Yes? How do you prove this result?
Using the commutation relation above.
Well, you just use it by expanding it out. Nothing else. You don't have to use any relation. All you do is just write this as xa into xbxc minus xcxb minus xbxc minus xcxb times xa. Write out all the three terms, just add, they will just simply cancel. Of course, this is because for us the product XAXB already has a concrete realization. It is in terms of, is defined to be XAXB minus XBXA for us. Although this is not my topic, but in the abstract theory of Lie algebra, you would say a Lie algebra is an algebra where you have a vector space and a product which obeys certain properties. And among those properties, Jacobi identity would be a defining property. For us, it's something you derive simply because for us XAXB commutator is the Lie product is really just the commutator. From this trivially follows. Okay. Now, if I just wrote this term in terms of the structure constants, let's just write down XA, XB, XC in terms of structure constants. So this is XA's commutator with this, right? Remember the structure constant is simply this. You take XA commutator with XB, you get I times F ABC XC, where sum of course is over C. Here, XB XC will be I F BCD XD. And this is just a number, so you can move it out of the commutator. Now you have a commutator between XA and XD. That gives you another I F ADE. So the two I's give a minus sign and you get F BCD F ADE times XC. Now why are we doing this? We are doing this because if I wrote this expression and repeated it by cyclically permuting B, C and A as we have done here, BCA, CAB, ABD, ABC, you must get 0, right? Because that's essentially the Jacobi identity. This is something which follows from this one. Yeah, so this is the structure constant. Okay, one property of the structure constant which we should have immediately written down is FABC is minus FBAC, right? Has to be because XAXB is anti-commuting. So if you interchange A and B, you must get a minus sign. And another property which follows from the Jacobi identity is this one. Okay? Right? So any questions about this so far? So in fact, we could even define a Lie algebra to be just a bunch of elements whose product is closed with the coefficients I, F, A, B, C. So whose product is a linear combination of the elements with these structure constants. But the structure constants have to obey this property and this property there. So if you are dealing with a mathematical theory of Lie algebra, reading a particularly mathematical book, you will find the Lie algebra is just defined this way. Okay? So now, this is going to be useful for many of you. So let's just take a look at this. Suppose I define an operator, a matrix. This is wrong. Let's just correct this. Let's define a matrix TA such that its BC element is given by this minus I F ABC. Okay, this is just a definition. So I've defined one matrix for every parameter. So if you have R parameters, you have R such matrices here. So what is the size of this matrix? How many rows, how many columns? Can anybody tell me that?
3 rows, 3 columns. I mean,
R rows, R columns, depending on how many generators you have. You said 3 because you are thinking of SU2, right? Or rotations. That has three parameters, but in general you have R parameters. So these are R by R matrices. And R of them. We have R by R matrices. Okay. But let's just take a look at what this relation becomes in terms of those matrices. This is TB's CD element, right? This FBCD. This is TA's DE element. Remember, there's a sum over D. So what is this really? This is the CE element of the product TBTA, right? Is that okay? I hope everybody can see the matrix multiplication here. Now, what about this one? This also has a TA somewhere, but there's one catch. You don't have CA in the first place, which is what you need, right? Or sorry, I just forgot to write the whole thing. Or maybe I wrote it and removed it. TABC is minus ISABC. That's the, okay. So this is TBCD, TADE, which is nothing but TBTA's CE element. What is this? TA's CD element, it would have been TA's CD element, but with a minus sign, right? Because you want FAC for that, and FACD is minus FCAD. And this is TB's TE element. Okay? Plus, now, okay, there's a minus sign here, a plus sign here, because of the two I squares, right? The F's are actually I times the matrix element. So there are two I's here, so you have a sign change. And now comes this FABD. Well, that's FABD. Let's leave it as it is. TD's C element with a minus sign. So, oops. I would urge you to carefully look at the signs, but this is basically what this looks like. But can you tell me then what this signifies? Why am I so interested in this equation? Yes?
It's the commutation relation.
So this is a matrix commutator now. So far the commutators we were talking about are commutators of generators, right? There could be some commutators of abstract operators, but right now we are talking of a relation which looks like this. If I move it to the other side, I get IFAB. So this is the CE element of IFABD TD. So on both sides, so I can just write this as ABD TD or ABC TC. So the important thing is that just by using the structure constants themselves, I have been able to write down a representation of the Lie algebra. That is, I have been able to find out matrices which actually obey the same commutation relation as was used in the Lie algebra itself. Right? So this is one representation, which representation is really a concrete set of matrices, right, as we have seen before, which for a group representation, the complete set of matrices have to obey the group multiplication rule. For a Lie algebra representation, it has to obey the multiplication rule, or here, which is of course the commutator. So here we have TA and TB matrices. Well, you don't have only just TA, TB, you have R such matrices. And for these R matrices, you have these commutation relation, which exactly mimics the Lie algebra commutation relation. So this is how the Lie algebra comes about. Okay. Now, the rest of the theory, of course, hinges entirely on this commutation relation. So I will just go through that. But I, of course, can't go through the whole rest of the theory. So I will just quickly look at some aspects which are important and which will be useful for understanding some of the stuff that you will see later. And this particular representation that we were talking about actually has another name. It's also called the adjoint representation. And here is another way of looking at the adjoint representation. And this involves something which I talked about in a previous lecture. Remember, when we say operators, they act on vectors, but operators themselves are vectors because they can be linearly combined. They form a vector space of their own. And so you can have operators acting on them. And one such operator, which we can define, or really not one, but you can define one operator for one super, like, wait, let's, just for the sake of simplicity of language, let's call these super operators. Okay, operators which act on operators, let's call them super operators. So for each operator A, there is a super operator add A. How do you define the add A? Well, add A super operator acting on the operator B gives you this operator, which is the commutator of A with B. That's it. Okay? Yeah? So now, what happens if you apply add A, add B in succession on some operator C? Some arbitrary operator C, you get this. Right? You add B first gives you a commutator with C. Add A gives you a commutator with A of that. And add B, add AC gives you this commutator. Right? If you subtract the two, of course, that's the commutator of add A, add B, right? If you subtract these two results, you get add A, add B minus add B, add A acting on C. So that's the commutator acting on C, which is, of course, the difference of these two. But now, let's just switch sign. This is ABC in cyclic order, right? ABC in some order. The cyclic order would have been BCA. But to get to the cyclic order, all I have to do is change the sign. If you switch A and C here, the sign changes, so you get a plus sign, right? But if you have these two terms, what is this? These are two terms in the Jacobi identity, right? It has to be minus the third term in the cyclic order, because this and this added together gives you 0. So if you have two of these, you get minus CA comma B, but that can be rewritten as this. But what does this tell you? This is the adjoint corresponding to A comma B to give you C, acting on C, right? Now, since this works for all C, it tells you that the commutator of add A and add B is actually the adjoint of A commutator B. So in a sense, commutator and adjoint sort of mingle with each other peacefully. You can either take the commutator first and then take the adjoint, or take the adjoints first, as I've done on the left, and take the commutator. Now, why is that important? It's important because if you start with generators of a Lie algebra, say you have x1, x2, x4, you have x1, x2 up to xr, and define these. I've just put a tilde on top just to sort of simplify the notation. So this xa tilde is nothing but add xa. So these are not operators really, these are super operators. Or they are operators acting on a different space. So what is the commutator of x tilde A and x tilde B? That's by our rule right now, it has to be add of xa comma xb. But xa comma xb is IFABC xc, and it should be pretty easy for you to convince yourself that it is IFABC commutator with xc as a result, so add xc. So what this means is whatever Lie algebra the original generators obey, the adjoint operators, which essentially tell you take commutators, obey the same Lie algebra. Okay? Yeah? And in fact, the adjoint matrices which we wrote down a while ago are really nothing but the matrix representation for this adjoint operator. Remember, the adjoint operators, where do they act? They act on the generators. So they act on an R-dimensional vector space. So the corresponding matrices will be R by R. Once you choose the generators themselves as the basis, you get an R by R matrix, which are the matrices I talked about before. Okay? So now I have no time left, so I will not go into all the details of whatever I wanted to talk about after this. But I will just talk about a couple of things perhaps.
Sir, can you please repeat the last statement you made?
Yeah, you can take some extra time also. It's
I will
not
take
a
some
very
around
big
10
deal.
15 minutes extra, I guess, but the next lecture has to start, right?
Sure.
Okay. I
Next
will take
lecture
some
is
extra
at 6
time.
o'clock. Yeah,
Yeah,
you
6
will get
o'clock.
some
So
extra
it's
time.
5:25. So I have some time. I will have to give them a bit of a break. Otherwise, I will get a oh,
Yeah.
okay.
Sure.
So what did I say? I said this. Uh, XA, XB are generators, right? So of the Lie algebra. So for example, I could, if I were talking of the defining generators for the rotation group, the rotation group is defined by the rotation matrices, by the 3x3 rotation matrices, right? So if I take a look at the 3x3 rotation matrices for infinitesimally small angles, say a tiny rotation about x-axis, tiny rotation about y-axis, tiny rotation about z-axis, that will give me 3 generators. And those generators essentially are the 3x3 matrix representations for the angular momentum algebra. Actually, those happen to be isomorphic to the spin 1 representation. But that's just an aside. That's sort of obvious. But anyway, that's true. But now comes the question. If I take the commutator itself, which is of course an operator which acts on these operators, so it's a different level altogether. These commutators also actually behave like operators which have the same commutation relation as the original generator, which is this is a consequence of Jacobi identity. So the adjoints give you a concrete representation, one concrete realization of the Lie algebra, and that is exactly what we mean by a representation. And if you, of course, this is an operator level representation. Of course, I've been calling this a super operator level representation. But once I choose a basis of the vector space on which these superoperators act, in particular, if I choose x1, x2, x3, xr as the basis, I will end up getting exactly the matrices that I talked about before. The TABC, the matrices, are really nothing but these. The matrices that you get out of x tilde A. So, remember x tilde A, if it acts on xb, I get IF ABC XC. Okay? So this essentially defines the matrix element for you. Actually, you remember the matrix. What should the matrix element for this be? When x tilde acts on xb? By definition, if you remember the definition of the way you get the matrix elements, the matrix element should really be IFA TB. And because you can define things in such a way that this is also antisymmetric, this is minus IF ABC, which is the definition I used a while ago. Remember here, x tilde is a fixed matrix. This is a bth basis vector. And when x tilde acts on the bth basis vector, you get a linear expansion in the basis vectors, and the coefficient gives you the CB term of the matrix element, right? So that's how you get to this. So all I'm saying is that the matrices that we considered earlier and this adjoint representation are really the same thing. They are just two ways of looking. One is the operator, the other is the corresponding matrix. Okay, one quick result that we may need to talk about is this. What happens when you change your basis? That is, remember XA, that is x1, x2, x3, xr, is just a basis of a Lie algebra, right? So you can equally well use a different basis. For example, instead of using J1, J2, J3, we often use J3, J plus minus, right? We do that very often. That's just a linear combination, an invertible linear combination of the original J1, J2, J3, and we end up with a different basis choice and different looking commutation relations, right? For J1, J2, you have this IJ3, whereas for J3, J plus, you end up with plus 1 times J plus. A very different looking set of structure constants. So one question would be that if I were to change XA by doing some linear transformation, so xa goes to x tilde a. Okay, I shouldn't really use x tilde because I've already used it for some other purpose. So xa goes to x prime a, which is some linear combination of this. And then we should ask what happens to the structure constants. That's an interesting question, but I'm pretty sure most of you can figure this out. So I'm not going to talk about this in great detail. Just to point out what will happen is something like this. LAC XC LBD XD. Then you get a LAC LBD out. These are just numbers. Of course, the sum over C and D are still there. XC XD. So you get LAC LBD IFCDE XC. But this is not a structure constant, because to get a structure constant, I should be able to expand this in terms of x primes, right? So for that, what you need to do is put in a and this whole thing, so the transformation rule for structure constants end up looking a bit more complicated than the standard transformation rules that we are used to. Sorry, x prime f. And this is going to be, apart from the I, if you leave the I out, or if you just write the I here, this is going to be f prime ABF. So, but this rule is actually quite interesting, and it can be cast in a neat matrix rule. So I will leave you to worry about this. How can you make this look like matrix multiplication in a way? And using this, you can get to some very special results. For example, you can get to results where you can choose a special basis where the matrices look like a particular form and so on. So those are important details, but right now I'm just ignoring all the important detailed steps. Let me just jump to one result, which is this, that, okay, one important thing is we would often talk about semi-simple Lie algebras as a special case. Or just, well, semi-simple comes after simple. Simple Lie algebras are simply Lie algebras which do not have any non-trivial centers. Centers are elements which commute in this case, commute in the Lie algebra sense in this case, with every element in the Lie algebra. If you had such a thing, then you would no longer have a simple Lie algebra. Okay. Semi-simple is something which may have a center but may not have an abelian center. Having centers actually makes the theory of representations quite complicated for reasons which are not very difficult, but again, I don't have the time to explain all that. But let me just talk about the general situation for a simple Lie algebra, which is, if you understand them, you can sort of understand most Lie algebras just by the same route as forming direct products. Okay, these are just words for the timings, but I'm just giving you the words to sort of give you a point of reference later, so that you can recall that, okay, semi-simple Lie algebras are easy to have construct representations for, and so on. So what do you mean when you say representations? You essentially mean something like this. You mean things like operators which will act on some states, and you want to figure out what the result of this actually acting on the states will be. Just to give you a point of reference, just remember that this is what we did talk about, right? For the SU2 case, or for the rotation angular momentum case, we talked about these extensively, even without using any language of Lie algebras, etc. We just talked about this, right? We figured out what J3 does to Jm, what J plus minus does to Jm, and so on. But before we go there, we even have to start with what Jns are, right? What specific states you're going to talk about. So basically, what you have is a situation like this. from your Lie algebra, which you have R generators, if necessary by taking linear combinations, you should be able to find a maximum number of operators which commute among each other. So and then you will have other operators. Right? What I'm insisting on is these operators commute among themselves. Now, an immediate consequence of this is, because the operators commute among themselves, their corresponding adjoint operators, add hi and add hj. What can you say about their commutator? The rule which I derived a while ago. So it's going to be adjoint with respect to the null operator, but that means take the commutator with the null operator, which of course is 0 always. So if hi hj commutes means add hi add hj commutes. So the super operators add h1 add h2 up to add hk, they commute with each other. Now if you have a commuting set of operators, and okay, these add his, who do they act upon? They act upon the generators themselves, right? But if you have a bunch of commuting operators, what does it tell you about their eigenvalues or eigenfunctions?
We can have simultaneous.
You can have common eigenvectors. It's not that all eigenvectors are common, but you can form a common set of eigenvectors. So basically, you can look at some, but remember the vectors here are actually the generators themselves or some linear combination of generators. So you will be able to find some linear combination of generators which are going to be eigenvectors of add h1, add h2, add h3, add hk. So this is what you're going to get, right? Now, of course, what does this mean? It means that you will find operators E alpha by linearly combining your generators, which will have this commutation relation with these. Okay, I should have given this a name. These operators, they then form something called the Karta subalgebra of my Lie algebra. The operators which commute among themselves. Once you have found the maximal set which commutes among themselves, you have found your Karta subalgebra. But once you have the Karta subalgebra, you end up with this result that you can find commutators with hi, commutators operators E alpha by linearly combining the generators in such a way that hi comma E alpha will be multiples of E alpha. Now this should definitely remind you of something, right? This should remind you of the fact that when you took J3 commutator with J plus, what did it do? It gave you J plus times 1 back. When you took J3 with J minus, give minus J minus back. So J plus and J minus were actually eigen operators or eigenstates of add J3. This is add J3 acting on J plus minus is actually plus minus J plus minus. And why is this so interesting for us? Because in any representation, what will J plus or J minus do? It will change the eigenvalue corresponding to J3. Here, what we have is this. First of all, if you look at the operators themselves, the generators themselves, what you have found out is that by linearly combining the generators, you should be able to find eigen generators like this, which essentially end up looking like raising, and not looking like, end up being raising or lowering operators for hi eigenvalues. And the final important thing, okay, not the final, but in any representation, you will have operators representing hi's, that is h1, h2, h3, and so on. But these operators will commute in every representation, right? Is that okay? Because In the original representation, the HIs commute. So in the original operators commute in the Lie generators. So in every representation, you will have operators which will commute. And so you will be able to find in every representation simultaneous eigenstates for them. In other words, have a vector relation like this. But now, what happens when you apply the operator E alpha on mu? Just think of what happens when you apply HI after you apply E alpha. You know what happens if you apply HI first? You just get mu I, right? What happens when you apply HI next? For that, all you need to do is just switch the order. But you can't switch the order because these two don't commute. But you know the commutator, right? So this is plus HI comma E alpha. And this is going to be mu I times E alpha mu plus alpha I. This is alpha I E alpha, right? So I'm not sure whether you can follow this rapidly. I'm just going through this pretty fast. But let me just remind you that this is exactly what you did to say that J plus and J minus, when they acted on Jm, they raised or lowered the J value, the Mj value. And that this is exactly what happens here. Same argument. Okay. Why does this happen? Because J plus J minus were had commutators with J3 which were multiples of J plus J minus. Here E alpha have commutators with HI which are multiples of E alpha. Of course, because you have more than one H here, unlike SU2 where you have only one Karta subalgebra generator, namely J3, you actually have a more complicated looking scenario. You have multiple indices. That's it. Other than that, nothing else happens. So basically, once you know these alphas, these eigenvalues in the original representation, these are called, the alphas are called the roots. The mu's which you get in some representation are called weights for that representation. But what you see is this. If you have a weight which is some k-dimensional vector, because it's mu1, mu2, mu3, mu-k, you add a root to it, it gives you a new weight. Okay. So there's a nice geometrical picture you can build out of this. Now, I don't have the time to contribute much more to this, but let me just point out one very important thing. E alpha and E minus alpha can easily show. If you take this commutator and take its commutator with HI and just apply Jacobi identity, you will get 0. That means E alpha, E minus alpha actually commutes with HI, but we already know what commutes with HI, right? The Karta subalgebra generators are the ones which commute with HI, and they form a maximal set. So what this tells us is E alpha, E minus alpha must be some combination of the HIs themselves. Okay. In particular, you can show, this is, I'm skipping the proof, but you can show that this has to be alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3. These alphas are just the same as this label. This label, remember, are the eigenvalues for the commutator. And you can easily use the Jacobi identity to show that this will happen. And finally, let me just quickly add this. What is the commutator of alpha HI with E alpha? That's easy. It's just you take an alpha I out, HI with E alpha is again another alpha I, so you get alpha square. Alpha I, which is the square of the vector alpha, E alpha, right? So if you look at this, if you look at these two equations, This should remind you of something, right? Here you have two operators whose commutator is the third operator alpha I hi, alpha 1 h1 plus alpha 2 h2 plus alpha 3 h3 and so on. And the commutator of this operator with E alpha is alpha square E alpha. The commutator with E minus alpha is minus alpha square E alpha. Can anybody tell me what this reminds you of? Three operators, E alpha, E minus alpha, alpha I, hi. And they have this commutation relation. The commutation of, so it's like A commutator with B is C, C's commutator with A is A, times a constant, positive constant, and C's commutator with B is a negative constant, times B. So what does this remind you of? Any algebra where you have seen this?
Angular momentum algebra.
This is exactly the angular momentum algebra with J3, J plus, J minus, right? All you need is, of course, there you need this to be a 2 and this to be plus 1, this to be minus 1. So that can be easily arranged by putting in a factor in front. That is, instead of E alpha, E minus alpha, just by choosing some multiplying factors, you can easily make this exactly mimic the SU2 algebra, the SU2 raising and lowering operators. And what's good is, for every eigenvector, that remember alpha is just, E alpha is one of the simultaneous eigenvectors of hi, hk, right? For every eigenvector, every simultaneous eigenvector that you have a raising or lowering operators in SU2, which essentially just raise or lower eigenvalues in a particular direction. That is, just adds these vectors. So I don't have any further time, so I will stop here. But I will just tell you that this is a fascinating subject, because after this, everything boils just down to SU2. If you know how to handle angular momentum, just SU2 operators, you essentially know how to handle any semi-simple D algebra whatsoever. All you need to know is you have raising lowering operators which look like spin-off, look like the SU2 operators and have the same properties. And just like in SU2, you know that you can go up in a ladder, you can go up this much and go down this much and not beyond that. That puts some severe restrictions on what kind of final representation you can have. So what kind of finite representation any such Lie algebra will have, all this structure can be deduced just by using the SU2 subalgebras which live inside them. So I'm not expecting you to sort of follow everything that I said right now. All I'm pointing out is, if you understand the SU2 algebra thoroughly, that is, if you understand angular momentum thoroughly, you have enough machinery in your hands to understand every Lie algebra. After that, it's just, if you have more than one SU2, so you have more than one direction you can move in, so it becomes a geometry problem, basically. And one case which is very, very easy to handle is SU3, because SU3 has two kata generators, which means kata subalgebra is two-dimensional. The great thing is you can always have the roots and weights all live in 2 dimensions, so you can have nice geometrical pictures of how you move in different directions. Everything happens in a plane, so it's nice and easy, and you can easily see whatever is happening. And you have actually seen what is happening. If you have taken the particle phase course, you have actually seen those multiplets drawn, which essentially are nothing but these SU3 representation states. So all this Mason octet or the Baryon decuplet or Baryon octet, all those, which many of you must have seen in particle physics texts, they are basically physical realizations of these geometrical pictures. For SU3, that's something you can draw in 2 dimensions, and that's why for SU3 those pictures are so useful. Okay, I will stop now because I've way run out of time, and I'm sorry that I couldn't really cover any reasonable part about what I wanted to, but I guess this is a good enough starting point. Okay, and while I wouldn't say George's book is very accurate mathematically or very general, but for physicist purpose, Georgie would be a good enough starting point. So if you want to read it, you could start reading that. Okay, I think I will take the organizer's permission to stop.
Actually, thank you, Professor Dasgupta. Thank you so much. Actually, you took a lot of pain and explaining these very basics of group theory. Any participant should get interested to read further with your this introduction. And we know this is a time constraint platform, and we have to do something within a particular framework of time. So even if we wish, we cannot really continue.
I understand all that because look, I have this bad reputation of rambling on and on and on. So I know that.
No, it is very required. Actually, I would like to tell you that it's an excellent series of talks, and I hope that students will keep contacting you looking for books.
Yeah,
now they have to
you can give them my email ID, for example, which is fine.
I will communicate. I will communicate
And
to all the.
Anyway, I think once you have the basics, you can start looking at standard textbooks and you can learn yourself. If you have any problem, you can of course contact me.
Yeah, sure, definitely. And thank you so much for spending so much of time. 6 hours is not a matter of joke. And actually, I would have loved to have this worksheet here. Then it is useful. Actually, when you are doing something sitting at home, lots of unnecessary disturbances come in. For students also, it's true, I know.
Yeah, that's true.
It's difficult for them to keep concentration unless and until he or she is very highly motivated.
And
so
of course, it's very difficult to follow when somebody keeps on saying something without any other real action. Teacher jumping in front of the board is actually much more entertaining than just looking at the screen. So I know, I understand all that.
For teacher also, it is very difficult. If you do not see the students you are talking to, as
the trouble is I keep on asking people to tell me things because I don't know whether I am getting through at all or not. At least when you're taking a class, you can see somebody's face and understand whether you are making sense or not. Here you can't.
In class, you can gauge what is going on, but here you can't. Really, you can't.
Well, I see that there are few of my students in this set, and they actually are sure that we don't know what is going on, but still. They have their own things that they do in classes, but still.
Yeah, still, it's very useful. It was very useful for me to forget about the students. So, thank you so much.
Thank you, but I think we must really wrap it up now.
So, we will keep that. And from the organizers, I would like to thank you again for being with us, for being agreed to talk to the participants in this workshop. It was a very important part of the workshop, introducing them to this whole important concept of group theory.
Yeah, let me finally say something that you have done a really fantastic job. I think I am heard about your this very good teaching ability from various of your ex-students, particularly Koshlendra Kumar, you remember probably with whom you went
for of course, he was something special, and I'm not very sure why he would say anything nice about me, because he was much more, he knew much more maths and physics than I did, but definitely more maths than I did. Koshlendra is really
but he was talking, he was very good. And he was also associated with me for 3 years or so, and we have written 3 papers together.
I know.
And he was always talking very highly about you, but I never had the good fortune of hearing your talk. But this is the first time, and it is very, very impressive. If I were a student at this age, and if I were to get a teacher like you, I think I would have thought myself very fortunate. So I again extend my heartfelt gratitude to you.
Now I'm getting embarrassed, so I'm just going to sign off. Okay.
So let's.
Okay.
No. Really fantastic job.
Yeah, she's really.
Anyway, I think we should let the students go because they won't have any time to rest. 5 minutes.
Yeah. So Professor Shulji will be here for 1 hour, so they will get a 10-minute break. They can have tea and come back. Okay then. Take care.
Thank you for having me.
Yeah.
Thanks, sir.
Okay, thanks a lot. You too.
So let's break for 5 minutes or so, not more than that, because Frederick will be there.